Okay, so if I'm not wrong, most of you are already familiar with Mathematica, and even if there is any of you who is not familiar with Mathematica, it don't matter much because Mathematica is pretty user-friendly. I mean, it's so user-friendly that if you move a few steps forward to make it more user-friendly, you are going to end up getting Jarvis from Iron Man, all right? So it's too user-friendly, to be honest. So, um, so using Mathematica as a new software is not going to be a problem if you are one of those who's new to Mathematica. And the topic we are going to cover today is solving partial differential equations using Mathematica. And technically, there are quite a few famous partial differential equations, for example, wave equation, heat equation, etc. So learning how to solve one of them would mean that you can solve any partial differential equations using Mathematica. But before I start solving PDEs, let me show a few tricks in Mathematica that we are going to need in today's lecture. So consider this part of the lecture as kind of an introduction to Mathematica. So Mathematica works like this. For example, if you need to solve an equation, all you have to do is open a Mathematica notebook like this, go to help, just click on all from documentation. A window will appear that looks like this. Type whatever you want to do. For example, if you want to solve equations, just write solve, press enter, and you will get a list of items that are closely related to your keyword. Let's click on solve. And it shows here that solve, the syntax for solve is this: solve, third bracket. This is a fixed syntax for Mathematica. Every function name starts with a capital letter, and you have to use third bracket for functions. The first argument is the expression, and the second argument is variable list. So here is how we actually use the function solve. I think this part is trivial to most of you. This is just for formalities. So say, for example, we need to solve the equation x squared minus 5 times x plus 6 equals 0. But like most other programming languages, while writing a statement or mathematical equation, you have to use double equal because single equal is already assigned for assignment. Okay. Now you have to write down the variable you are going to solve the equation for. So our variable is x. Now you have to press enter. There is an interesting fact about pressing enter in Mathematica. In most keyboards where you have two enter buttons, one on the numpad and one on the alphanumeric part, if you press the enter on the right side of your keyboard, the one that belongs to the that is part of the numpad, you have to just press enter. That's all. But if you press the other enter, the one that we generally use most often, you have to press shift and then enter. In most laptops, we do not have two enter buttons. So in case of a laptop, if you're using a laptop, just press shift and then enter. You will see something. Can you see the screen, or do I need to zoom a bit? I think I better zoom. Is it visible to you now? Please confirm something.
It's okay.
Okay. So, so you can see that you already know the solution of these equations 2 and 3. So you can see the list of the solutions. But there is an interesting structure of the output. You can see that the output is a set of sets, and each of those sets inside the original, each of those sets, each of the two sets inside the original set contains the solution, and not in the form x equal to, but x approaches to. There is a reason behind it. I will explain the structure later, and we are going to make use of this structure of the output anyway. Now, we are going to need to define user-defined functions. In Mathematica, everything works as a function. The solve command is also a function. Its first argument is the equation we need to solve, and second argument is the variable we are going to solve for. So just like that, if we want to define functions by ourselves, it goes like this: f of x. Just write a simple function, f of x equals to x. And this will not work if you write f of 2. Generally, you expect that the result should be 4, but it is not going to work, because while introducing or writing an user-defined function, while defining, we have to write an underscore after each variable. So now the compiler understands that this is where you are defining a function. If you press enter now, you can see that in the first line, the function, this is the output of the first line. If you write a semicolon here, like most languages, it will not show x squared, and that's it. You can differentiate, integrate, etc. In Mathematica pretty easily. For example, if you want to differentiate, the command is just d, and the structure of it is d of the first argument is the function you need to differentiate, and the second argument is the variable. So if you just write d f of x and then the variable, it will give 2x. Interestingly, Mathematica actually never finds the exact derivative, but the partial derivative. Let me explain or show how. Let's define a two-variable function, one underscore at the end of each variable inside the argument list, equal, for example, x cubed plus, say, y square plus, say, x squared times y. So this is the function. Now, if you write d g of p comma q, and if you write the variable x, what Mathematica is going to do is, okay, there is no x inside the expression g of pq, so let's write p here. So what it does is it differentiates the expression g of pq with respect to p partially. It keeps q constant. And there is one more thing. If you just wrote g of 1 comma 2, it would give the exact result. Right? It works straightforward. Well, another feature I want to show about Mathematica is there are some very likable library functions in Mathematica. For example, Fibonacci 5. It gives the fifth Fibonacci number, which is 5, right? Just like this, you have another function, prime 3. It gives the third prime number. And also it has a function prime q. And if you input a number, it gives true or false, depending on the number being actually prime or not. You can search, just write, go to the help browser, go to the Wolfram documentation, write prime. You will get a list of every function that's related to the prime numbers. But what I'm interested to show you is, if you write 10 here in the Fibonacci function, it gives the 10th Fibonacci number. What if I write 100? It's a huge number. Now, what if I'm interested to see the thousandth Fibonacci number? It's a huge number. But now I'm a bit interested to know how far it can go. So that's why let's increase another 0 in the argument, and you can see that this is the 10,000 Fibonacci number. And if I add another 0, so the library functions can give you pretty large numbers, to be honest. So this is an interesting feature of Mathematica that I like very much. Let's get 10. Okay. Now let's see how arrays work in Mathematica. All right, so let's define a set S where I list a few numbers, 1, 2, 3, 4, 5, 6. So if you just press enter, it gives the since there is no semicolon after the statement, it outputs the entire list. Now, if you want, say, for example, the fifth member of this set, generally you would go for S5, excuse me, S5, but this does not work. Why? Because third bracket is particularly assigned for functions. So to distinguish between array index and function, you have to, this is the syntax, you have to write 2 third brackets. If you press shift and enter, you get the fifth member of the set. But here is where it gets interesting. If I replace 5 by another set, 10, 11, 12. Now, what should the output be according to your common sense? It's exactly that. Here we have a set within a set, and it considers the entire set inside the set as the fifth member of S, and it outputs the entire set. Now, maybe you are interested, this is a nested situation, right? A nested set. We can say this is a nested set. Now, you may be interested in this particular number 11. That is, the fifth element itself is a set. You are interested in the second member of that set, that fifth member. So how do we do that? It's pretty easy syntax. Just write 5, 2. So S5 means the fifth element of the original set S. And since that guy is already itself a set, if you write just comma and 2 and press enter, it gives the second member of that set. It's taking a few seconds. Okay, so here's 11 as an output. Now you can go as far as you want. You can just replace 11 by another set, for example, 9, 8, 7, 6, 5, 4, 3, 2. So if you enter now, the entire set 9 to 2 is here. If you are interested in 7, just write a comma and 3 after 2 here in the index. It gives 7. So this is how indexing works for sets within sets within sets in Mathematica. And we are going to make use of this feature. Let's see how. Let's get back to the original solve command. Let's copy this and paste this here. Okay, Mathematica has this interesting idea that it can save everything in a variable. This solution can be saved in a variable as well. For example, A equals. It means now if you write just A, it gives the solution. You can even save a graph in a variable. Everything can be saved in a variable in Mathematica. This is an advantage of using Mathematica. Okay, now let's get back to where we were. Now the solution is presented in a form where it is actually a set of sets, right? So A is a set of sets. If you write A1, what should appear? I think you guessed it right. The first solution, the first set. Now, if there is another, now A1 is itself a set. And in this set, there is one member, right? So if you just write 1, 1 here, you get the member inside the first set, which is x tends to 2. Now, Mathematica considers this guy and this guy as set elements as well. This is very interesting, even though there is no set sign. So if you just add a comma here and add 2 here and enter, you get 2. If you had 1 here, you'd get x. Did you get the idea? Mathematica considers this expression, even though this does not look like set from any angle, but Mathematica considers this as a set, and the guy on the left of the arrow is the first member, the guy on the right of the arrow is the second member. So if you are ever interested in the second guy, for example, the only value 2, you just do this. In many cases, we may be interested in actually using this syntax of indexing syntax, because sometimes you write codes that are that contains multiple lines, and maybe you are writing a line after the solve command where you need the first solution only, not the set of solutions. Then you have to write a code segment like this so that you can extract the exact integer solution or real number solution 2 from the structure of this expression. Okay.
Sir, can you please use a new line every time you demonstrate a new thing so that we can understand what changed and how the input changed and how the output changed?
Okay. I think I got the idea. Just let me know if this is exactly what you wanted. If you just write A1, you get this. Now, if you just add comma and 2 here, what happened?
I think it's
Okay, there is no
a 1, 1, right?
Okay, now copy this again and add comma and 2 here. It gives you 2. I think this is a good suggestion, to be honest, because you can observe them separately. Okay. Now, so at the beginning of my lecture, I told you that I'm going to explain why the team Mathematica team chose exactly this structure for giving you output of the solve command. Everything is explained except the arrow sign, the tends to, right? It will be explained later. For now, let me show you another syntax. Can you recall, if you do not, there is a command called exit. If you do not use that command, all the lines executed previously will be saved. So if you just write f of x, there is no expression because I think somehow I exited somewhere. So let me rewrite the function. F of x equals x squared plus 1. Say, for example, I'm going to use this function, f of x equals to x squared plus 1. Now, a situation may appear where arise where you are trying to replace the variable by a value. Now, for a function, it is straightforward. What you do is just write f of 2. It will give the expression of x squared plus 1 by replacing 2 in place of x. But sometimes, if you are writing multiple line codes, it's inconvenient to replace the entire function. So sometimes we need something like this. For example, we already shown how derivative works. F of x differentiating with respect to x. So this is 2x. Sometimes we do this. Write a slash, not backslash, but slash, then a dot, followed by an expression inside a set where the expression, the expected expression is x minus greater than, which will become arrow the moment I press space bar, just like this, and say, for example, 2 or 5. If I execute this line, I am going to get 10. What the code segment does is replace this entire expression, replace x by 5 everywhere inside this expression. Now the derivative was 2x. It replaced x by 5 everywhere inside the function. If this was a multivariable function, you could write multiple expressions. For example, x tends to 5, comma, y tends to 10, etc., etc. Okay, this statement is called replace all statement. There is an alternate function for this as well, but this is more convenient to use. Now, in most cases, when you solve something, in many of those situations, you may be interested to replace this solution somewhere. That is why the structure of the solution contains x tends to 2 and x tends to 3. For example, maybe maybe I want this. Maybe I want the inside the derivative, I want to put x equals to the value of the origin. Where is the equation? Okay. Maybe I need the solution, the first or second solution of this equation to be substituted in the expression here in the expression of the derivative. What I'm going to do is just write a 1, which means the first solution, comma 1, which means the expression x tends to 2. If I write just enter, it replaces, the function was twice x, right? It just replaced x by 2 and gave 4. So we might be interested in using statements like this. That is why the Wolfram companies decided that, or the engineers decided that this should be the ideal expression for the solution. Okay, please let me know if there is any question so far. I will share this notebook file with you, and also the recording of the video. Okay. Now,
Sir, can you please remind me why do we need to use f of x underscore?
Okay, I think this is one way I try to explain this this idea, that generally if you do not write this, it already consider, for example, f of 4. Whenever you write this, Mathematica thinks you are trying to input 4 inside the expression of the function, replace x by 4 and give the output. But even if you write this, Mathematica understands that you are trying to replace the variable by the value a. So Mathematica considers this to be a parameter directly. So there is no way Mathematica can distinguish between this expression and this expression. If you just write f of x, Mathematica thinks that somewhere a function is defined where you want to replace the variable by the parameter x. So to make it distinguished from this idea, they need to use some sort of difference in the syntax, and I think they added this underscore for that reason. Whenever you write underscore, Mathematica understands that you are trying to define a user-defined function now, not assigning variable equals to x. Was the idea, was it clear?
Yes, sir.
Okay. Now let's move on to a topic of a slightly different flavor. For example, let's see how plot works. We have already declared a function f of x equals x squared plus 1. Let's plot that function. You could write sine function, cos function, or any other function, known functions as well. Just try to follow the syntax that the first letter must be capital. And the syntax for plot command is, the first argument is the function. The second argument is a set that contains the variable name followed by the minimum value of the variable followed by the maximum value of the variable inside the range you're trying to plot. So if I press enter, I get this. Now, as per the suggestion by Orko, I'm going to copy the command and show some other ideas. For example, there are some attributes I can add to the plot command. One attribute is plot style. The most commonly used attribute is plot style. Whenever you write plot style, it will suggest the value of the attribute. And say, for example, if I just press dashed and press enter, it gives the same plot dashed. Now, if you want to add multiple plot style, whenever Mathematica uses multiple attribute values, this is the same common syntax here. Just use a second bracket, and instead of a single attribute value, just write a list of attribute values. For example, if you write orange here, you are going to get a dashed orange curve. Let me check if I can add thick here now. Yes, it works as well. And if you just go to the help browser and search for plot at the bottom of the page after the examples, you will see many of these extra attributes list there. I think, and as I said, everything can be saved in a variable in Mathematica. So let's name this plot to be Z. So if you now just just write Z and press enter, it gives the same plot. Everything is saved inside the variable, right? Another kind of plot is list plot. To demonstrate how list plot works, let's write a set S equal 10, 20, 30, 40, 50. And another set T equals 11, 12, 13, 14, 15. So let's see how list plot works first. From the name, I think you guessed that what a list plot is. If you just add a list of pairs here, it plots the first, by default, it assumes that the first variable is to be plotted in the x-axis and the second variable is plotted on the y-axis, and this is how it works. For example, there are examples here. Okay, let me show here. List plot, for example, if we have a point 1, 2, 2, 10, and 3, -5. I think it's expecting set of sets here. What it does is plots 2, y equals to 2 when x equals to 1, and so on. But sometimes, let's cut this from there and paste here. But sometimes we are in a situation where we need to use the list plot for data like this. The first variable contains all the x values. The second variable contains all the corresponding y values. If you try to use list plot, for this data like this, for example, s comma t, it is not going to work. Why? It shows error, right? Because it's not in the format, the argument is expected, right? We need to make pairs of 10 and 11, then pair containing 20 and 12 and so on. How to do that? First of all, if you just write second bracket and s comma t, then you can, let's write semicolon for these two lines so that, no. Okay, so you can see that this set is here. It is a set of sets, but it's still not in the format we need it to be. So for that, let's just write transpose. And I think that's an intelligent way to convert it into what we need. So this is exactly what we need. Now you can just save this transposed set of sets in a variable and just write k here and enter. Now you have a plot of the list. Now you can add attribute for list plot as well. For example, add comma and plot style and say thick. So then maybe use another color, something more vibrant, like so we have used orange here, so I think something like, I don't know. Okay, they have cyan, one of my most favorite colors. So okay. Now sometimes you need to show two plots in one graph, and there is a command for that, and the command is just show. So we have already saved our graph of x square in the variable z. Now let's save this list plot in another variable set w. So show z and w, and voila, you have both graphs in the same plot, but you cannot see anything because the range of values for x goes up to 50 for the list plot, but it goes up to 1 for this. So to avoid this, what we need to do is add another attribute called plot range and select all, press enter, and do the same for the list plot as well. So plot range all. So now if you rerun the show command, you can see both graphs here. Only the problem is the orange curve is okay. There is another solution for that. Let's just write -10 to 10 here, run this segment, and then run the show command again. Better. So this is how you can show multiple graphs in one. There are other ways to show. My suggestion would be just browse the plot command in the help browser and look for different attributes. Things will be clear to you. There are many options. Okay. And before moving on to solving partial differential equations, one last thing: how loops work in Mathematica. For loops has this structure. It has 4 arguments. The first argument is the initialization. The second argument is the condition. Next argument is the increment, and the last argument is the statement of the loop. If you run this, it looks like this. If you want to add multiple initial conditions, then all you have to do, you guessed it right, just add a second bracket here because you are trying to use multiple input here. and say, for example, write j equals 10. And if you just write j here, it is going to print 10 4 times. If you write j plus plus, the other things are like typically you use in other programming languages. Here, the printing is done first, then the increment. You already know that if you write plus plus on the left and run, then it increments j first and then prints, etc., etc. These are common, just slightly different syntax for the for loop. Now, let's see how we solve differential equations. Start with ordinary differential equations first. So the command for that is dsolve. Let's write a pretty straightforward differential equation. Derivative of y as a function of x with respect to x equal y. Every time you write y, you have to write bracket x also. And we need to solve it in terms of x. So here, what I wrote here in this highlighted region is simply y, derivative of y with respect to x. Or in other words, dy by dx. In the highlighted region, I just wrote dy by dx. And on the right hand side, I have y. So dy by dx is equal to y. This is a pretty straightforward differential equation. And the solution is doable in your mind, right? I think most of you already solved it. Okay, what happened? Okay, the syntax contains the dependent variable also. So 3 arguments. The first argument is the differential equation you are going to solve. The second argument is the variable you need to solve for. And third argument is the independent variable. If you run the code, it gives. It looks weird if you write the constant, arbitrary constant on the right, but it's still covered, right? Okay. Now, maybe you have initial condition. So initial condition. Okay, let me show another thing. In case of derivative, if you need the second derivative, what you need to do, let's move back a few steps. Where did I show derivatives? Okay, here. Here I have derivative of the function x square, which is termed as f of x with respect to x. But the first derivative, if you ever need the second derivative, all you have to do is put a second bracket around x and comma, write 2 and done. Is the second derivative. If you write 3 in place of 2, it's going to show 0, right? So this is the syntax for higher order derivatives. So if you just write comma 2, if you just write this, the differential equation is now changed. It now looks like d square y by dx square equals to y. I think just add a minus here. It becomes the differential equation of a particular simple harmonic oscillation. And the solution is as expected, right? 2 arbitrary constants, C1 and C2. Let me copy this first equation again. Okay. Now maybe you have initial conditions. So initial condition is another equation alongside the differential equation. That is how Mathematica sees it. So just add second bracket here. The differential equation itself is the first equation that Mathematica needs to solve. Add the initial condition as the second equation. Maybe the initial condition I'm going to add is y at 0 equal 5. Now, you can understand this is too trivial for you. The solution should be 5 e to the power x, right? As expected. If you try to solve a partial differential equation using Fortran or any low-level language, it would be significantly more difficult than the algorithms for regular ordinary differential equations. Because the numerical method algorithms are difficult for partial differential equations. Multiple variables are involved. That's one way to visualize why it's going to be more difficult. There are other issues as well. But in case of Mathematica, partial differential equations and ordinary differential equations are pretty much same, because the command D already, you know that this is partial derivative. If you wrote multiple variable functions here, if you wrote x here, it would mean partial derivative with respect to x. So it looks similar when you solve partial differential equations. So just let me let me connect my graphics tab, please. Give me a moment. Let's start with a simple differential equation. So the first differential equation we are going to solve is del u by del x equals to 4 del u by del y. Okay. So let's try to solve this partial differential equation first. Del u by del x equals to 4 del u by del y. So let's copy this command. Let's not copy. Solve derivative of u as a function of x comma t with respect to x equal 2 times. Now let's copy this expression. But now with respect to t. Is it the equation I wrote earlier?
আর 4 times মনে হয় হবে 4 times
4 times del u by del y. I wrote t, but it's y here. So let's write y here, 4 here, y. And we need to solve in terms of, okay, we need to solve for u. So second argument is the variable we need to solve for. So y. And the third argument is the list of independent variables, x and y. Should work. Okay. If you already solved a few partial differential equations, you already know that in case of what happened? Okay. As I was saying, if you already solved a few partial differential equations in PDE course, then you already know by now that in case of an ordinary differential equation, you have arbitrary constants, but in case of partial differential equations, you get arbitrary functions. So here the solution is C1 of 4x plus y equals 0. It's not shown here that C1 of 4x plus y equals 0 is the solution, but you can understand. So C1 is an arbitrary function of x and y here. 4x plus y here. Any arbitrary function of 4x plus y is going to satisfy this equation. Now, if you add initial condition here, just like IV ordinary differential equation, add a second bracket here, close the second bracket here, write a comma, and add the boundary condition as just another equation. So maybe the boundary condition I'm going to use is u at 0 comma t is equal to 8 times e to the power, there's a function for that, exp, minus 3 times y. I wrote this particular initial condition, boundary condition with this particular partial differential equation because this problem, this is an exact problem from Shom's outline series. I'm solving this one so that I can verify if my solution is correct. There is something wrong somewhere, and here it is. I have to write double equal here.
Also, e
Okay.
of 0 comma y, right?
Oh, again, 0 comma 1. Okay, so in the last case, we got C1 of 4x plus y. But here we got the exact function. There is no arbitrary function involved anymore because I have used this condition with my PDE. So I think I should write two separate equations here as opposites. That will be easier for you to understand. So as you can see here, we had the solution in terms of an arbitrary function C1 of 4x plus y, but here that we already got that exact function. So that's how it works. Now let's move on to an actual heat equation. The general heat equation actually, give me a moment, please. I don't want to make any mistakes, so I'm going to copy from the textbook. So the general heat equation has the structure del U by del T equals to a square. The square is to make sure that we have a positive constant here. Del square U by del x square. And with some initial conditions and boundary conditions. For example, if the boundary is for x, if the boundary is something like this, and generally you consider that time is not going to be negative, so t greater than 0. Generally, it's expected that you are going to be given a function of u at the two endpoints, x equals to 0 and x equals to b. So U means heat energy here actually. So the heat energy travels through time and space. For example, maybe you have an object that looks like this, and we have written x here but no y or no z. So the actual object we are considering here is theoretically just a line and one, for example, a one-dimensional rod. So this is x equals to 0. This is x equals to b, and you're applying a heat source in a way that at time t equals to 0, you know the expression for u of x. That is, at time t equals to 0, you know what, this is the initial condition actually. You know where the value of the heat energy at every point on the line or on the rod, and then you're applying a heat source somehow so that you are maintaining a certain heat level. Maybe that's variable, but that may not be constant. But that the fact is the expression is known at these particular 2 points. So these are the boundary conditions. So this is the initial condition, and these are the boundary conditions. And this is the governing equation following which heat travels. So if you solve this, you can get at the end, if you can analytically solve, of course, you are going to get an expression of heat, the level of heat energy as a function of x and t, so that you can know the level of heat energy at every point on the rod at any time given. So this is the idea of a heat equation. Now we are going to consider a certain expression for a particular case, for example, del u by del t. This is also from Shom's book. The source doesn't matter much in this case actually. The name of the book is Advanced Mathematics for engineers. So this is the name of the book by Shom series, and this particular problem is page number 266, problem number 12.16. But the source doesn't matter. I'm just okay. So I'm choosing this particular example just because the problem is already solved here. I searched for a random problem that is already solved, and so that I can compare my result in Mathematica with the solution in the textbook. That's all. There is no more significance to it. So del u by del t is twice of del square u by del x square, and u0t equals u3t equals 0. So the two endpoints of the rod are kept at 0 temperature. Technically, U does not really stand for temperature as far as I can remember. It represents energy. So ux0. Okay, please correct me if I'm wrong in this particular case. I'm pretty weak at physics. According to my memory, U represents energy, but Nian corrected me. He said it represents the heat flux actually. Okay, so U represents heat flux. So heat flux is 0, and ux0 is 5 sine 4 pi x minus 3 sine 8 pi x plus 2 sine 10 pi x. And the only extra information given is U is bounded inside the time and space given here. Okay, so I'm going to solve this problem now using Mathematica. So let's start. Desolve. So the left hand side is del u by del t. So d derivative of u as a function of x and t. And now you know why I was mistakenly writing t again and again. With respect to left hand side is derivative by del t, right? Equal, right hand side is 2 times d u as a function of x t, comma, now with respect to t, but of the order 2, second derivative, right? So this is the equation we are going to solve. Put the equation inside a second bracket because we have multiple conditions along with this one.
On the right hand side, shouldn't it be x comma 2? Not
Oh, right.
Uh,
Yes. Thank you. It's x comma 2. Del square u by del x square, right? Okay. The boundary conditions are u 0 t equal 0, one of on the left boundary. The right boundary condition is u 0 x equal not really, it's 3t equal 0, and the initial condition is u at x 0 equal a huge function. I have the textbook in front of me, that is why I'm just copying from that. 5 sine 4 times pi times x. I can just copy this expression now. 5 sine 4 pi x minus 3 sine 8 pi x plus 2 sine 10 pi x. 10 here. 2. Okay. Second argument is the variable we are going to solve for. So u of xt. Third argument is the variables xt and run. Should take a few moments, and it did not work. Somewhere a problem. Supplied equations are not defining. Okay, du xt t. Okay, let me do a troubleshoot by exiting first. Let me cut this from here. Let's exit first. Sometimes it happens. I don't know if this is the problem, but let's check. Says running. It's running. Okay. So this was indeed the problem. We have used the variables multiple times in multiple places. So something got mixed up. So I just exited the code so that every variable is cleared. Now copy pasting the same equation and running, we get this particular solution. Now let's save this solution in a variable SOL. Okay. Now let's try to plot the function so that we can see how u changes with respect to x and t. And plot, we used plot for single variable function. We have 2 variables here. For that we have plot 3D, a command called plot 3D, which works exactly like plot, only this time the graph would be a three-dimensional graph. But there is one problem. The problem is we want this expression as a function to plot. How to get this expression? We have already explained how to do this in today's lecture earlier. Just write solve. First of all, let's see what we get right in solve 1, and you get this expression. So you have to write comma 1 so that you get this expression, but we need this part. One way to do this is just write comma 2 and you get this. Another way is, this is one way. And maybe and let me show you another way. Solve 1 1. First write this. Now you can just use can we use replace all command? So in this expression, I'm going to replace using basically this is the rule I'm going to use. So what's the expression? So let's use the expression uxt, and in this expression everywhere use this rule. The part after the dot is called a rule. This is the rule we are going to use to replace. This is another way to get the function. So we have seen both of these techniques earlier in today's lecture. You can use any of them. So let's see. Maybe basically this, so far this is an expression. This is not a function. We are not ready to put values of x and t in the expression. So for that, we are going to declare a function, maybe solution function of variable x underscore comma y underscore equal this. So, and we could do the same using this one. For now, let's keep this one. So let's use just this array indexing method. So now we have declared a function solve fun, and I think instead of y, let's just write t. Okay. So now we have a function that we can use in the plot command. So write plot 3D solve fun is the function that we are going to plot in variables x and t. Okay. And just like plot command, we need to specify the range of values of the variable x, but here we have two variables. That is why we need to use another list here containing the variable name t, starting point again, say -1. You can understand that the expression of the solution contains pretty huge magnitude, numbers of huge magnitude, right? So taking t equals to some slightly bigger negative number would cause the solution to burst out, right? So we do not want that. So does it work? Let's see. If it doesn't, I have to browse the help browser. I hope this works. 3D plotting takes some time. Some really long time. Okay, very weird looking function, right? So this is how we solve the
দেখতে মনে
PD.
হইতেছে যে
Yes, please.
স্যার ওয়েবের মতো লাগতেছে weird.
Basically, this happened due to the weird initial condition. That's all. Okay. Now, to summarize, we just learned how to solve the PDE using Mathematica with initial and boundary conditions. Good one. Fine. And we learned how to plot that solution. Now there is just one thing remaining. Maybe we are slightly interested in the general equation more than a particular equation. That is, let's add a parameter here instead of a particular number 2. So let's see what Mathematica does in that. So let me copy the previous copy. Let's exit first. That's one thing you may need to do multiple times if you do multiple codes in one file. So I just exited. Every variable is cleared now. Now I'm copying this part of the code. Control C, Control V. But instead of 2, I'm going to write a parameter A here. We already have used A somewhere earlier, but that variable is cleared now. Shouldn't be a problem. So now if you enter, it's running. You can see that now you have the parameter inside the expression of the solution. Mathematica does this pretty well. Mathematica handles parameters pretty well. It gives you solutions in terms of parameters pretty easily. Now let's copy this part here. So you have the expression as a function of x and t, but you also have the parameter a here. Okay, Fahim suggested something. I will see that later. But if you now need to plot using this command, it's going to be a problem. You should understand, you should be able to understand why. Because plotting works like it actually plots exact points, but the points are going to be in terms of a. So depending on the value of a, the plot actually depends on the value of a. That's the straightforward reason, right? So this is a problem. So what we can do in such situations is use a command called manipulate. It's an interesting command. This is how it works. For now, let's leave the plot command and just write manipulate. The syntax looks like this. Copy the plot command from here. Paste here. Now, instead of directly using solution function, use replace all here, and the rule for the replace all is going to be a tends to some parameter k. You are using another parameter name because a is already used. Use a different name, for example k. So we are replacing a by k. And you can see that the manipulate command is expecting another argument here. We have a red arrow here. And here, just write k comma, say -1 comma 1. So what this function does is puts different values of k varying in the range from -1 to 1. And the plot updates real time. Let me show you how. Just run the code. You see a graph like this, and you can see that we have a controller here, a control variable k here, and the lowest value of k we have assigned is -1, the highest value is +1. So we can just increase the value. It may take a little bit of time. It will update after that. So increasing value of k, it looks like this. If this was a 2D plot instead of a 3D plot, the update would look really live, to be honest, in real time. But here, since 3D plot takes some time to plot, That is why after changing the value of k, we need to wait for a while to get the update. And if you put k to some it's updating real time now. Okay, so if you put a value of k that is close to 0, you can actually move the graph also. To be honest, you can see from different perspectives and angles using your mouse, so that you can see the effect of varying value of k on the solution function. So this is an interesting feature of Mathematica. I think that would be all. This is all I made for today's lecture, and please let me know if there is any confusion anywhere. The stuffs are easy actually, because it works like a very high level scientific calculator, right? Just paste the expression of the equations and just press enter, and that's all. So should be pretty straightforward for you, but still, if any of you have any questions, please let me know.
স্যার এই পার্শিয়াল ডিফারেনশিয়াল ইকুয়েশনে কোশ্চেনটা একটু দেখা যাবে কি ছিল কোশ্চেনটা?
Okay, Tanmoy requested for the original question problem we solved. This is the problem we solved actually. Did you ask for the one with the parameter a, or the actual specific problem?
No, this one.
Okay. You have any question here?
I just wanted to see the problem.
Oh, okay. Are you done?
Thank you, sir. Yeah.
All right. Okay. All right. Anyone else? Any more question?
Sir, I have a question that's like not related to today's topic.
Okay.
But I think previously I forgot to submit assignment 3, and then I think I submitted it on November 26th. So like, just in case if you missed it.
Please give me a text in Discord regarding this topic. All right, we shall discuss there.
Okay, sir.
Okay. Any more question related to the lecture?
স্যার আমাদের তাহলে এখন স্যার ম্যাথমেটিকে ডাউনলোড করে তারপর অ্যাসাইনমেন্টটা সাবমিট করবো স্যার। অ্যাসাইনমেন্টের টাইম কতক্ষণ থাকবে স্যার?
Okay, now Fahim asked if all right, yes, you need to download and install Mathematica. Basically, the assignment problem I'm going to provide today is going to be a 10-20 minutes problem, or even less, because you can see that there is not much of coding to be done. But I'm going to provide longer than that anyway, because you are already bamboozled with other projects and assignments, right? So maybe I'm going to provide about a 24 hours window. I'm going to Fahim asked if you can use Mathematica online. Yes, you can use Mathematica online. The code is all I need, and it would be, I would prefer the notebook file. The Mathematica program files are called notebook files. The extension is .nb. I would prefer .nb files more, to be honest. So it's better if you download.
Okay, sir.
Okay.
So I think we can export notebook files as well from online.
Okay. That's even better. You can use just Mathematica online and export the code as a notebook form and upload through the Google Form link. All right. I have not made the assignment problem yet. I'm going to post it within 30 minutes after I end this meeting. And I'm going to give you about 24 hours to submit the assignment. Today's assignment is going to be pretty easy, actually. Okay, if you guys do not have any more questions, I'm going to end the meeting.
And also the notebook. You promised to give us this notebook.
Yes. I'm going to share this particular notebook with you also. All right. All right, okay, that
Sir,
would-
please share the original, the problem that you actually solved here.
here, I mean, right now or in Discord?
No, I mean, when you share everything, please also share the actual equation that you solved on this.
All right, I got your point. I'm taking a screenshot from the, I think.
স্যার আমি স্যার তুলে রাখছি স্যার স্ক্রিনশটটা এটা
Okay, I'm going to provide it anyway. So give me a moment. All right, is there any more question? Okay, then I think we can leave the meeting now. See you all on maybe Thursday, right? We have a class on Thursday, right?
ইয়েস
Yes.
স্যার ইয়েস স্যার
And
হ্যাঁ
I think
yes.
also on Friday because they scheduled extra classes to cover up the lost week, right?
Yes, around 5 to yes.
Sir,
Okay.
from now on, do we use Mathematica from now?
Yeah, from now on we are going to use Mathematica. Maybe
Then whatever-
yeah, sure.
Then whatever the final exam,
Whatever, I didn't get you.
well, whatever the final exam, do we use Mathematica in final exam?
In the final exam, I'm going to provide problems that may require to use both softwares.
Oh, okay.
Okay. Okay. All right. See you on Thursday. And all right, that will be all. Thank you.